So the last speaker of the session is Dovi Poznanski, faculty at Tel Aviv University, School of Physics and Astronomy. Previously, Dovi was here at UC Berkeley as a postdoc, and he'll be talking about finding needles in an astronomical haystack. Hopefully, he'll be finding what an astronomical haystack is.
Yeah, so it's sort of a cheap analogy, the haystack, but you'll see soon why I sort of had to use it. Thank you. I'm glad to be able to present this work here. I'll explain the title as we go along, why real or bogus and why the 2.0. First thing, I think this project is really at the core. It's work I started doing here in Josh's group, the Center for Time Domain Informatics, and it's really a very natural project for that center. And you can see from the list of collaborators here at Berkeley that it includes people from staff department and computer science, and from astro, because it's a project in astronomy, and really all those different people contributed a lot to various aspects of this work. Because often these projects happen differently. You have either machine learning experts that get a bunch of data they don't really understand very well, and they just play with it and use their knowledge of machine learning to do the best they can on classification. Or you have astronomers in that case that have data that they know very well and understand very well, and they just download some package and use it and classify. And here we really try to get experts from both sides and try to do the best we can. But what is the problem I'm talking about? So in transient surveys, in astronomy, we look for things that change often, and I mean, in the things I'm interested in and many people are interested in. And the way we do it is by just imaging big chunks of sky, and we subtract every new image from an old image. And this allows us to basically correct from changing settings between the two images. But this subtraction is difficult. The images are often very low signal to noise, and the action of subtracting those images, even when you adjust for the different conditions, is far from perfect. And this is getting to be a bigger and bigger thing as bigger and bigger imaging devices are becoming available. We already have pretty big surveys running now, and there are much bigger surveys planned. And to get a sense a bit of the data, so here's a pretty typical, I actually picked a totally random image. And what you can see here, I think, is most of one CCD. I'll put that in context in a second. And this is a template image. So when we subtract, we actually don't subtract just one other image, but actually a combined image of a few older ones, which gives us more depth. And you can see here that indeed you can see more objects on this image than this. It's the same part of the sky, but the density of sources is higher because the image is deeper. It goes to fainter objects. You subtract, and what you get is something that looks like this, and you see that there's a lot of junk on that image, a lot of things that are not really valuable, but just you do subtract perfectly. And you can see it better if I zoom in on a smaller chunk of it. So again, it's the same image just centered on a specific object, and you can see the template image again, and you can see the subtraction, and this is a real source, and all these are not. And that's really the question. How do you find the real source out of all the things that are not? And I said this is a small piece. What I'm showing here is a small piece of one CCD. In the survey of which data I'm talking about today, the Palomar Transient Factory, our camera has 11 of those CCDs. And we image about basically a new image every minute and a half. So every night we have hundreds of these times the 11 CCDs, and that ends up being about more than 1 million, sometimes 1.5 million candidates per night. Basically things on the image that could be real, but are most likely not. So those Josh coined very early on when we started working on it at Bogus, and I really like the term, so I stick to it. So there's subtraction artifacts of all sorts of reasons, cosmic rays, which actually doesn't really matter, but it's something that's not a real astronomical sources. There's still a variety of reals. There are many, many asteroids out there in a given out of that million, really rough numbers, we're talking about 50,000 and about 1,000 variable stars. And I'm specifically interested in supernovae, in stars that explode. There are about 50 of them in one night's data, but only 1 or 2 that are really young, new objects that we're interested in discovering that we haven't found in previous images. They've just happened. Those are the ones we want to get. So how do we find that 1 or 2 interesting objects out of more than 1 million that we get per night? And this is really the needle in the haystack problem. And again, this is for a survey that's much smaller than things that we will get very soon. So the first effort, and that explains the 2.0 in my talk, so the version 1.0 was led by Josh when we started our involvement in PTF, in the Palomar Transit Factory. The basic idea is we looked through the data, we found a few hundreds of sources, and then we've used them to build a machine learning classifier. And you can see here the interface, the web-based interface on which a bunch of us went online, looked at the objects, looked at some numbers about them and some extra data, and sort of decided whether it's really astrophysical or bogus. And we went through tens of those, many people, and you could combine. I've erased mostly the names. This is basically the difference between the scores a person gave to a candidate compared to what the average of all of us said. And you can see that some are actually experts. They actually know what they're doing. And you can see that they're spiking at 50, which is what you expect, which is basically they agree with everybody else. Some are overly pessimistic. Some are overly optimistic. They think everything's real, everything's great. And obviously, you can do all sorts of very neat combinations of those things and weigh people up and down. If you see that they're really good at predicting what other people are saying, you can correct for their biases. So that's a nice way of combining all that information, and you can basically get a score, and that's the RB score, the real bogus score. And you can see that most objects get very low scores, and a few get very high scores, and that's the combination that gives you something. So that approach is basically what's being used now for PTF. That's what we're using. That's what allows us to be actually a very successful survey that has found thousands of supernovae and published many papers, and it's great. But we want to do better, and there are a few problems. First of all, it's difficult to get many people to do that kind of work. Second of all, it's very difficult to find many objects for them to look at, to basically build a large training set. One way to do this is to use asteroids. And the idea is that we know they're around there. There are many of them are listed, and we can basically predict where they are, so we can go there. And then we know that thing is real because it's on the list of known asteroids, and it should be there at that time. So this is, again, a plot that Josh made that shows the real bogus score versus the brightness. So basically, all you need to know is that this is bright and this is faint, even though the numbers seem to say the opposite. That's the magic of astronomy. And you can see that most of those sources, so this is a completely independent testing set. Most of them get really high real bogus scores, and only a few really are basically misdetected. The problem, obviously, is that this doesn't show you the amount of false positives. Another thing you can use is the hive mind. So this is another project that was along those lines of how to do better, and that is using the platform of the Galaxy Zoo, a group of people in England who were doing galaxy classification using crowdsourcing. They really like the idea of joining in and do the hunt for supernovae. And I have numbers that are pretty old, but there were users there who've done 20,000 classifications for us. Basically, people at home who, for some reason or another, don't have something better to do and find that exciting and contribute to science. And that's pretty much where our project here kicks in, and what I want to talk to you, and is really how we can beat all those different things. And what we really wanted to do is systematically examine all the steps involved in finding whether an object is real or bogus. and build the ultimate cookbook for PTF, but also for future surveys. Again, thinking that this is going to be a big deal. Now, the whole development process is extremely non-linear. In order to think what kind of data you need, you want to be able to try and classify it. So you need to pick a classifier. In order to pick which classifier you'd rather use, you want to have some data. So there was a lot of, I'll just say this, if my plots are not super self-consistent, it's because we haven't just done the full through of everything, of all the different things that I'm describing in a very linear sense, but we're actually very iterative in the process. And I've added this. We really have, I mean, I should say when we compare everything to real Bogus 1, is that we have the gift of retrospect. We have a lot of data. We know what we've done. And that allows us to do better. So the first stage is really to build the training set. And I think that's where we had quite a few insights. Picking up Boguses or Bogi was easy because we have a database that has about 1 billion of them. So we just pick as many as we wanted. And by just picking random things that we know are not reals, we're probably picking mostly things that are bogus. There is some question in this. There will be some contamination. I'll get back to it in a few slides. How to pick up reals is not as easy. But we do have, at the time, we took all the data from 2010, so we had about 600 supernovae that were discovered during that year. But every supernova that was discovered at a given time, using real Bogus 1 and previous methods, was also observed often a few days before, and hasn't been detected. Perhaps it was too faint, or perhaps it was too difficult, or nobody really looked at that data. And it's been observed since, as it goes and becomes brighter and fainter and conditions change. So we can look at all those detections of that one object and really, in some sense, de-bias ourselves from the things that a previous classifier could find. And that also gives us multiple detections. Basically, we have 10,000 individual detections of 600 supernovae, and the rest are various different types of sources, variable stars, active galactic nuclei, etc. So we are biased towards the kinds of objects that PTF people care about, but it doesn't really matter much in the sense that, in the end, what we're looking for is things that look like that and not like that, which seems rather easy, but obviously as the signal to noise goes down, it's less obvious. These are relatively bright real sources, and are relatively easy to recognize bogus sources. Of course, this one, and some of these where you can see that the subtraction didn't go perfectly, and you have some positive and negative residuals. So that was step 1, to build a training set. Step 2 is to extract features. Again, a lot of work has happened about that before. The thing we've found is that really coming up with new, very fancy features that describe the boguses doesn't help us much. They're very diverse. Their shape is difficult to capture in simple features. But the reals are simple. I've shown them to you. They just look like point sources. They just look like small Gaussians. And by fitting a 2D Gaussian to the residuals and basically tabulating the width and the goodness of fit of that Gaussian, we do get a dramatic improvement. So in terms of feature extraction, ooh, I gotta go faster. We didn't come up with tons, so I'll skip this. The data, as I told you before, is extremely imbalanced. We are talking about 1 million candidates versus 1 or 2 interesting objects or a few tens of reals. So we've examined the question of the ratio between bogus and real. What do we want to feed the classifier? And you can see that actually our classifier does best. This is some metric, the figure of merit we have, which is basically the misdetection rate at contamination, at the false positive rate of 1%. And you can see that actually the line that does best is the one that has a ratio of 1 to 1. So actually, we found that training with the same number of reals and boguses does best. You can see here how nonlinear the problem is. You can see basically it's impossible to see what are the features. It's all written way too small. But you can see that when you compare the samples of real and bogus, the features are really messily combined with each other. We tried a bunch of different classification algorithms. We ended up using random forests. We're happy with the speed and with the way it works. We spend a fair amount of time thinking about feature importance. Basically, what you can do here is a backward search where we're throwing away features one by one and seeing what happens to our figure of merit. The same misdetection rate at 1% false positive rate. And you can see that actually by throwing away some features, we do get better. We are less confusing the algorithm and getting better results. Obviously, when you throw away all the features, you're not doing very well. Another important aspect is that, as I said earlier, the boguses were just a random sampling from the database. And that must include many reals that we've never detected, we never knew were there. We've actually found that the label cleanliness, the fact that we're teaching our algorithm to work, to recognize the real from the bogus on a sample that's dirty, is actually not a big deal. The contamination level we have is not significant. And this is, I think, a very important thing for any future survey, because what it basically does is completely remove the human bottleneck from the process. You don't have to look at tens of thousands of objects, or you don't need thousands of people to look at many objects. Because as long as you have some process that can give you some decent level of purity, then that's good enough. But obviously, if you want to end up with a good evaluation of really the contaminations level you're getting and the real detection rates you have, you need to clean the subset. But this is much easier. You can see here a comparison of the ROC curves. So this is the false positive rate, misdetection rate, and this is the number we were aiming for. The reason is that typically we get more than one observation per night. And if we get 2 observations per night, and assuming, it's actually a wrong assumption, but it gives you a starting point, that the boguses are uncorrelated, then a 1% false positive rate, if you square that, gives you 1 in 10,000. And out of 1 million candidates, that's just a number you can actually cope with. It's a number you can actually look at every night and decide that they're bogus and throw them away. And you can see this is sort of the benchmark we started. This is RB1. And this is the improvement. And you can see that actually adding the features we've added didn't add much, going from, so this is the blue and red curves, from using all the features or using the features that were in RB1 and with our own training set. You can see that basically the improvement comes from having a much better and larger training set. Again, they had a few hundreds and we have tens of thousands. But if we also add the subset using only the optimal features from the feature selection, then we do even better. And you can see that the improvement is dramatic. From basically missing a third of the objects, we're only missing 1 in 10 or 1 in 8. So this is a pretty big improvement. And we're working now and finalizing also some aspects of what I mentioned, the fact that we have more than one detection a night. And there are correlations, as I said, but we can sort of have a second layer machine that uses the information from multiple detections and combine that and gives us an answer at the end of both observations. So the main conclusions, I think, from that project is that, well, like many learning things, you want to have the biggest sample you can have. And that's not too surprising, but the fact that it can be a dirty sample is actually a very useful and important result. And you can bypass the human bottleneck with survey overlap. Basically, I mentioned that what we did is we used what the survey did a year before, but a new survey that starts can basically just overlap for a short amount of time during their commissioning on the same area as another survey and use all those detections. And basically, this will give them very quickly a training set that they can use, and it's a lot easier than using humans to go over the data for nights on end. The best features, as I said, are those that describe the real sources, but really, we didn't get tons of improvement from new features. Most of it was just from bigger and nicer training sets. And a last thing I haven't said, but is worth mentioning, there's really no computational challenge in this problem. The numbers are not big. The computational part, even retraining is not a big deal. It takes a few minutes on a desktop computer. So that's not where the big computational challenge in astronomy lies. But definitely a lot of thinking is still to happen. That's it, thank you.
Any questions?
Is there any more detail you can share with us about exactly how you did the feature importance graph? More specifics on how you decided which feature was important.
So we've had many iterations on that, and what I'm showing here was a selection where we basically start with all the features, train, etc., try it on a test sample, remove one feature, basically remove all the features one by one, just every time, just one of them, and see which instance gives the best score. And then we pick this one, we throw away that feature, and we do the same thing again. Remove all the features, ask where do we get the improvement, and continue. There's many questions. There are many correlations between the features, so the order in which you do it are non-trivial. We've spent a lot of time talking about it. We tried many things. So actually one thing I skipped and I can mention in that context, which we came up with as a trick to see if actually feature selection makes sense, is that we added those two features. One of them is empty. It's 0 for all candidates. And the other one is random, which is just a totally random number. So the first one should be non-informative, and the second one should be just noise. And what you hope is that random will be thrown away first because it does damage, that empty will be thrown away pretty quickly, and their position in your throwing away order should tell you which features are actually nasty, which features are useless. But we've actually haven't fully implemented it yet in the feature selection plot I've showed, so I can't really tell which features are. But I think it's a nice trick to get a sense of how well your selection is working.
So I had a couple of questions. The first one is, did you have any input into or feedback for the actual subtraction itself, or was that just a given?
I'm not sure I understand the question. I mean, we started with the actual images by pulling out the postage stamps on the actual subtraction image.
You performing this on subtracted images, so did you actually perform the subtraction throughout?
As in, can we improve the subtraction?
Oh, you mean using it as a sort of loop to improve the subtractions? Is that what you're asking?
Well, did you do the subtractions, or was that by somebody else?
Well, it's sort of us and not us. I mean,
Okay.
it's collaborators, friends. It's all within the collaboration. So I could easily repeat the subtractions, change them, but we were treating it as an input.
Okay, and the second question was, so he's saying that the mislabeled examples in the training set didn't have much of an effect. Was there a particular reason for that? And also, does that have implications for example, galaxy classification and mislabeled examples in that sphere?
So, it's a good question, and I don't have a really good answer. I would obviously say that the reason it's not important, it's probably because the numbers are not that big. The number of reals within the Bogus set are pretty small, and vice versa. How small? We didn't try artificially changing it and adding and contaminating it more. We're mostly worried, do we have to look at those 60,000 now and with them? Because that's just untractable. And we're surprised we didn't have to. So we have some estimates on the impurity. And basically the impurity is pretty much the rates I was showing earlier. So we expect a few tens of thousands at most out of a million to be real. So that could be fairly substantial. And yet it wasn't enough to alter our results.
One more quick question.
So what was the fraction of the real objects in the test set? So what was the ratio between real and bogus on the sample?
So as I showed in this figure here, we tried with different things, and we ended up seeing that looking at one-to-one.
That was in the training set.
Yes.
So how different was the ratio between real and Bogus in the test set?
We've had many test sets, so I actually am not sure which. Joey, if you want to try and answer this one, you're welcome to.
My real question is that how similar was the ratio in the training set and in the test set, or was there a skew?
So we fixed the total training size to be 20,000 out of 60 or 70,000. So it's just a complement of that as a testing set. We haven't tried just holding out a fixed testing set and doing it. The thing is, in the real data, the real to Bogus ratio is quite low. Right. Okay, let's thank Dovi again and all the speakers in the session. So the last speaker of the session is Dovi Poznanski, faculty at Tel Aviv University, School of Physics and Astronomy. Previously, Dovi was here at UC Berkeley as a postdoc, and he'll be talking about finding needles in an astronomical haystack. Hopefully he'll define what an astronomical haystack is.
Yeah, so it's sort of a cheap analogy, the haystack, but you'll see soon why I sort of had to use it. Thank you. I'm glad to be able to present this work here. I'll explain the title as we go along, why real and bogus and why the 2.0. First thing, I think the totally random image. And what you can see here, I think, is most of one CCD. I'll put that in context in a second. And this is a template image. So when we subtract, we actually don't subtract just one other image, but actually a combined image of a few older ones, which gives us more depth. And you can see here that indeed you can see more objects on this image than this. It's the same part of the sky, but the density of sources is higher because the image is deeper. It goes to fainter objects. You subtract, and what you get is something that looks like this, and you see that there's a lot of junk on that image, a lot of things that are not really valuable that just didn't subtract perfectly. And you can see it better if I zoom in on a smaller chunk of it. This project is really at the core. It's work I've done, I started doing here in Josh's group, the Center for Time Domain Informatics, and it's really a very natural project for that center. And you can see from the list of collaborators here at Berkeley that includes people from staff department and computer science, and from Astro, because it's a project in astronomy, and really all those different people contributed a lot to various aspects of this work, because often these projects happen differently. You have either machine learning experts that get a bunch of data they don't really understand very well, and they just play with it and use their knowledge of machine learning to do the best they can on classification. Or you have astronomers in that case that have data that they know very well and understand very well, and they just download some package and use it and classify. And here we really try to get experts from both sides and try to do the best we can. But what is the problem I'm talking about? So in transient surveys, in astronomy, we look for things that change often, and I mean, in the things I'm interested in and many people are interested in. And the way we do it is by just imaging big chunks of sky, and we subtract every new image from an old image. And this allows us to basically correct from changing settings between the two images. But this subtraction is difficult. The images are often very low signal to noise, and the action of subtracting those images, even when you adjust for the different conditions, is far from perfect. And this is getting to be a bigger and bigger thing as bigger and bigger imaging devices are becoming available. We already have pretty big surveys running now, and there are much bigger surveys planned. And to get a sense a bit of the data, so here's a pretty typical, because